Welcome to day 8 of calculus. We're going to learn about how we can analyze limits numerically and graphically. So we will be evaluating these types of expressions. Right at the top here, you'll see this thing. It's this thing which we've written in many times already in class, and you read it as follows. The limit as x approaches c of x is L. The limit as x approaches c of f of x is L. It means that as the x values get closer and closer and closer to c, f of x, the output value, gets closer and closer to L. So numerically, the way we can analyze limits is to make a table and to test values really close to the left and really close to the right, and also the trail as we get closer from the left here and from the right over here. And all we're doing here is we are filling in a table. So we're looking at this function right here, x squared. What happens to it as x goes to 2? What happens to x squared as x goes to 2? And the way you can test that using your calculator is you can just plug these values into your calculator into this function right here. So the most direct way to do that, the most direct way, which many of you will do first off, is to literally do 1.9 squared and press enter, and you get 3.61. And then you could do 1.99, same idea, and end up with these answers. So I did the next one, 1.999. So 3.9601, 3.9601, and then the other one was, so you really can just manually plug it in. So the first way is to just do the function repeatedly. A quicker way is to enter the function and then evaluate the function at those numbers. What I mean is this. On your calculator, you go into y equals and you enter the function. In this case, it's y squared. Go back to the main screen. I'm going to clear it here. And if you go into vars, y vars, enter function, and enter again for y1, you can call the first function, which is x squared, and then plug in the number you want and press enter. And then you can do the same thing. It's vars, y vars, function, enter, and then you can do it with, oh, I hit it twice there, sorry. Plug in 1.99, and then hit enter. Another thing you can do is hit second entry, and it brings back the last entry, and then I can go back here and just type in another 9, and you get the same thing. Now, it doesn't seem like this saves too much time with comparing it to how we did it before, but if the function was more complicated, like x squared plus 2x minus 9, or kept going, it's much faster to do it this way. I recommend this way if you're doing a few values like this. So if we want to go to the right values here are 2.001, 2.01, and 2.1. We can go back to the calculator. It's the same function, so we go vars, y vars, enter, enter. Let's plug in 2.001. We plug that in, we get that number. I'm going to do second entry, go back, and I'm going to delete one of these zeros, enter, and then second entry, and I'm going to delete the other 0, like this. Oh, look at that. So there they are right there. So if you look at this trail now, what does it look like? As x gets closer to 2 from the left, as x gets closer to 2 from the right, it looks like these numbers are getting really close to 4. So based on the paths they are making. Now here's the thing. You might look at this and you say, well, can't you just plug in 2? Well, in this case you can, but you can't always plug in the c value. You can't always plug in the c value. Instead, you have to make trails like this on tables. So you can either do it directly or with setting the function equal to y1. So you can't always plug in the c value. So in this case, the c value on this one is x goes to 0. So the c value is 0. So if we're looking at what happens as you go to 0, a little bit to the right would be 0.001, 0.01, and a little further would be 0.1. This would be negative 0.001, negative 0.01, and negative 0.1. So those are numbers to the left and to the right of 0. And if you use your calculator or just do it out by hand, you'll find that as you're approaching from the left, the numbers get really negative and big, and if you approach from the right, they get really positive and big. They get really positive and big. So you could say the limit as x goes to 0 from the left of 1 over x is negative infinity, and the limit as x goes to 0 from the right of 1 over x would be positive infinity. So let's do one that's a little more complicated. Well, the c value here is 0. You can't plug in 0 into this because it's in the denominator. So we're going to use our calculator to make a trail of values. The first thing I'm going to do is I'm going to enter this function, the function right here, into my calculator, like so. Then I'm going to go back to the main screen. Remember, with vars, yvars, enter. So remember, it's vars, yvars, enter, and then y1. And then we're going to evaluate the function we entered at y1. Our first value was right over there, negative 0.1. So negative 0.1. We plug it in, and you can hit enter. And then you could do it again. Remember, vars, yvars, enter, enter. Should really practice that to know where it is, negative 0.01. So these are our first two values. We go enter. So after you use your calculator, you can see that from the left, it looks like it's getting really, really close to 2, and from the right. So this one looks like as it goes to 0 from both sides, it's going to 2 from both sides. So you couldn't plug in 0 into this expression, but using your calculator and filling in the table, you can see that the limit from the left is going to 2 and the limit from the right is going to 2. Wanted to show you one other way to fill in this table, and what you can do is that you can actually make a table on your calculator. Above the window button, right, there's table set. So you go second window and you go to table set, and you tell it where you want the table to start. So in this case, we want to start maybe at 1.9. That's the number we want to start at negative 0.1. So you go back to here and you start, let's say, negative 0.1. So how much do we want it to increment by? How much do we want it to go up each step? Well, we can do it every 0.01, every 1/100th. And now see how there's table right there above graph? You go second graph. And look what it does. At negative 0.1, it's 1.9. And then as it gets closer and closer here, look what happens. It's just going to be error because you can't divide by, oh, look, there's 2.01. Now, if you want to get even more accurate, or smaller steps, you can go into table set and you can change the table, delta table, to 0.001. You can do that. But now when you do this, let's start it at 0.2 there, so we can go back. Let's start it at, how about start it back at negative 0.1. If we started it there, it's going to go up, but then you have to keep clicking a whole bunch to get all the way to where you want to get to. So you can jump around and fill this in, but it really looks like it's approaching 2 from the left and 2 from the right. Table set's really great when you have an even jump, but these right here are not even. You can use it for parts of it though. So again though, you get there by going second window and then telling it where to start the table. So in this case it was negative 0.1 and what the delta should be. So maybe you can change it to 0.01. And then it's second graph, so it's table, and then it starts the table where you want and at the step you specified, with the step you specify. So now let's figure what the limits are from a graph. So what this one says right here is, what's the limit as x goes to 0 from the left? As you approach 0 from the left, what is the output, f of x? So as you approach 0 from the left, so 0 is right here. So as you're approaching that on the graph, so you're an ant on this graph, you're approaching, and let's just say this goes like this. You're approaching. As you approach 0 from the left, meaning the x value is going to 0, what's the output value? What are you getting infinitely close to here? You're not going to, remember, the 0 is going to 0, sorry, the x value is going to 0 from the left. It's never actually going to get to it, but it gets infinitely close to, what does that output look like? How high does it look like that point is? And it really looks like it's going to 0. What happens if you come at it from the opposite direction, from the right-hand direction, which is the second one? As x goes to 0 from the right, meaning you're on the function as you are moving towards 0 from the right, what's the output going to right here? What output is that? So as you go from the right and get infinitely close to 0 here, on the x going side to side, that's the x values, how high are you? Well, you're going to get infinitely close to 2. So you'll notice now that this just says, what happens as x goes to 0? What this means is it is a number if it's the same from the left and right, and it said not to exist if it's different, not to exist if it's different. So let's take a look at this first one. I, as you approach 2 from the left, as you approach 2 from the left. So 2 is right there. So as you're approaching 2 from the left here, you're getting, it looks like it's infinitely close to 4. That's 2 from the left. What about 2 from the right? 2 from the right. 2 from the right gets infinitely close to 2. This is the left-hand limit, that's the right-hand limit. They are different, so this one does not exist. And you can say D and E, that's totally fine. So we've made a table to analyze limits. We have looked at a graph to figure them out. Now let's look at them algebraically. Lots of fun here. The first thing you need to remember, is whatever you're approaching, in this case x is going to 2, you check to see if you can plug it into the function itself. Can you plug in 2? Absolutely. This is just going to be 2 times 2 plus 4, which is 8. You always check to see if you can plug in the number first. Can you plug in -1 here? Can you plug in -1 into this function? Sure. 3 -1 squared plus 2 times -1 minus 1, 3 times 1 minus 2 minus 1, so it's 3 minus 2 minus 1 is 0. Always check to see if you can plug in first. This one though, you can't plug in 2. 2 is not in the domain. If you do factor this function, let's factor it a little bit. So it's x goes to 2 of x minus 2 over x plus 2 times x minus 2. The domain is x such that x can't be 2 or -2. So you can't plug in 2 to the original function, but if you simplify, and as we know, when you simplify something like this, all you're doing is plugging the whole, which is fine in terms of the limits. With x goes to 2 of 1 over x plus 2. Now, can you plug in 2 into the simplified form? You absolutely can. It's going to be 1 over 2 plus 2 is 1 over 4. What you've done by canceling, as you know, is find where the hole is. You've plugged the hole, and if you've plugged the hole, it doesn't change the limit of approaching to the left and right of that hole. So the answer to this is found by simplifying and then plugging in. So if you can plug in the number, awesome. You just plug in the number, and that is what you get is the limit. Over here, if you can't plug in the number, you try to simplify and see if you can cancel and then plug in what you're approaching. So we couldn't plug in 2 into the denominator because we'd end up with a 0 in the denominator, and that would be an indeterminate form. There are others. Other indeterminate forms include something of the form 0 over 0, or some form of infinity over infinity, or infinity times 0, or infinity minus infinity. You can't assume anything about those. You need to simplify what you get first before you deal with anything that is an indeterminate form. Anything that is an indeterminate form, you need to simplify first and do some analysis. You can't just plug in and assume infinity minus infinity is 0. That's not necessarily true. So on this one, remember, just like with all limits, you ask yourself, can you plug in what you're approaching? Can you plug in 4 for h? And you can't because of the denominator. You can't create an indeterminate form, a 0 in the denominator. So you look to, can you factor? Well, not yet. So because we can't factor this nicely, there's nothing really nice to pull out, let's multiply it out. h plus 2 squared multiplies out to h squared plus 2h plus 2h plus 4, and then there's still that minus 9h, and this thing is still over h minus 4. So how many h's do we have on top? We have 2h, 2h, and minus 9h, so that's minus 5. So you end up with the limit as h goes to 4 of h squared minus 5h plus 4, and then over h minus 4. We haven't changed anything, we've just multiplied out. Now, though, I think this is nicely factorable. So what's this going to be? The limit as h goes to 4 of h plus, is it h plus 4? I think it's going to be h minus 4 times h minus 1 over h minus 4. The magical thing happens now, and we can cancel, leaving us with the limit as h goes to 4 of h minus 1. Now, can we plug in 4 into there? And that's h minus 1. Yeah, we sure can. So that's just going to be 4 minus 1, which is 3. So if you can't plug in initially, do some algebra. Might be some factoring, might be some multiplying out, might be some combination, and then see if you can plug in. Well, let's check. Can you plug in 0 into this one? Well, no, because you'd end up with an indeterminate form of dividing by 0 right there. So we need to rearrange this. We need to do something to this without changing the overall value that gets it to a point where we can plug in 0 for h. We need to multiply everything by the same thing. Keep that in mind. So for example, we could start by saying, well, let's multiply everything. So we're going to multiply this by 3 over 3. Multiplying by 1 doesn't change anything. So the 3 gets multiplied into both of these things and down there. So what do we end up with? 3 over 3 plus h plus 3 over 3 over 3h. Okay, well, what does that do? Well, this 3 over 3 becomes this just becomes a 1. That's nice. How about we now multiply by 3 plus h over 3 plus h. Again, this is just a form of 1. This was a form of 1, and this is a form of 1, so it doesn't change the overall value. We multiply in all the places, and we end up with 3 times 3 plus h over 3 plus h plus 3 plus h, because that's 3 plus h times 1. And then the denominator is 3h times 3 plus h. Well, what happens here? That cancels, and you're left with a 3 plus this 3 plus h all over 3h times 3 plus h. And you might have caught the small mistake here. There's a minus sign there. It's right up at the top. And that makes it so this is actually doable. So now we take that and change it to a minus sign. And if we do that, this is a minus 3 plus h. And that makes all the difference. So now when we simplify this a little bit further, we end up with 3 minus h all over 3h times 3 plus h. Well, what cancels up there? The 3's go away, right? And you're left with negative h over 3h times 3 plus h. Oh, what cancels? The h's cancel, and you're left with negative 1 over 3 times 3 plus h. And remember, we're doing the limit as h goes to 0. 0, right? I think it was 0. Yeah, it's 0. 0 of this thing, negative 1 over 3 times 3 plus h. Well, now, can we plug in 0 to h? We sure can. So this is going to be negative 1 over 3 times 3 plus 0. So it's negative 1/9. So you have to do algebra to the point where you can actually plug in for the limit. This one looks visually nasty, but all you're really doing is searching for some form of 1 to multiply it by to make something that's quote-unquote nice, something that makes it so you can plug in 5. Well, can you plug in 5 right now? If you plug in 5 for h, you get 5 plus 9. The square root of that is 3. 3 minus 3 in the denominator would be 0. So we can't plug in 5. So what we're going to do, and the hint is this thing called a conjugate. Conjugate means something very specific. The conjugate of a plus b is going to be a minus b. But remember, we have to multiply by a form of 1, so we have to multiply by the same thing on the top and bottom. Our problem, quote unquote, is the denominator. We kind of want to clean that up. So what would the conjugate of that be? It would actually be the square root of h plus 4 plus 3. And you have to multiply in the same thing on the top and bottom because you need a form of 1. This is just a fancy way of writing 1. So what do you end up with? Why is this really nice? Well, when you multiply this out, it looks like it's nothing's being helped here, but look at what cancels. These middle terms cancel, and then when you multiply the square root of h plus 4 times the square root of h plus 4, you get h plus 4. So what do you end up with? Well, you end up with these two multiplied together to get this, and the 9 carried down right there. And you'll notice I have not multiplied out the top. You'll see why in a second. So you want something to cancel. So let's multiply, we'll simplify the bottom, and the top stays the same. H plus 4 or plus 3 all over h minus 5 in the denominator. Our new denominator is now here. And what's so nice is this now cancels, leaving you with the square root of h plus 4 plus 3. And remember, it's the limit as h goes to 5 all the way down. So now, can we plug in 5 into this? We sure can. You plug in 5 and you end up with the square root of 5 plus 4 plus 3. It's the square root of 9 plus 3, which is 3 plus 3, which is 6. So the whole key was you had to multiply by a form of 1, and the form of 1 came by looking at the denominator. What's the conjugate of that? The conjugate of the denominator here is the numerator here and the denominator there. So let's cruise through a couple more examples here, and when you see this, you might think to yourself, oh man, this isn't that bad, because you know what, I can factor. And at this point, after you've factored difference of squares here, we want the same denominator to be able to add or subtract fractions. So if we have x minus 1 right here, we need to add in the x plus 1, but if we add it in the denominator, we're going to need to add it in the numerator. So what you do is you multiply just this one by x plus 1 over x plus 1. And then what do you end up with? Remember, we haven't changed anything because this is just a form of 1. It's just a form of 1. Our denominator is the same in both. right here. Denominator is the same, so we kept it the same. And then the 2 is there, the minus 2, and then you just have x plus 1 right there. But what does that numerator simplify to? Well, it simplifies to this, which is awesome because guess what cancels? The x minus 1's cancel, leaving you with the limit as x goes to 1 of 1 over x plus 1. Now you ask yourself, can I plug in 1? Can I plug in our target right there? And you sure can. It's going to be 1 over 1 plus 1, which is 1 over 2. So we did some algebra, and in this case we combined fractions and we cancel. Oh, this was the magical thing right here. So nice. This one looks so nice and straightforward. There's that square root of x. Can you plug in 4? No. This is another one where you have to multiply by the conjugate. And you might be tempted to multiply by x plus 4 over x plus 4. But let's try doing this instead. The square root of x plus 2 over the square root of x plus 2. We are allowed to do that because, again, this is just a fancy form of the number 1. You have to be very careful when you multiply this out. So when we do, keep the denominator the same. And the hint there is that we want to eventually be able to plug in 4, which we can't because of this. So we eventually want to cancel that. So let's leave that like that. Let's now multiply out the top. When you multiply it out, you have root x times root x. And then you have plus 2 root x minus 2 root x. And then it's minus 2 times 2, which is 4. These middle terms cancel. And the square root of x times the square root of x, this term right here, turns into just x. So the numerator is x minus 4, and the denominator stays x minus 4 times the square root of x plus 2. And it's the same limit as x goes to 4. What's the magical thing that happens? They cancel, and you're left with the limit as x goes to 4 of 1 over the square root of x plus 2. Now, can we plug in 4? We sure can. 1 over the square root of 4 plus 2. It's 1 over 2 plus 2, which is 1 over 4. Nice. So if you can't plug in the number, simplify to a point where you can.